In this video, we'll do another increasing, decreasing concavity example, and we'll use that information to draw a sketch of our function. All right, so in this example, we have the function f of x, which equals x to the 2/3 over 6 minus x to the 2/3. And I'm just going to say what the derivative and the second derivative are. So here they are in factored form. And in part A, I want to find the intervals where f is increasing and where it's decreasing. In B, I want to classify the critical numbers as being local maxes or local mins or neither, and find the local extreme values. So first, I want you to pause the video for 4 minutes to try this question. 4, 3, 2, 1, pause it and try it for 4 minutes. Alrighty, so hopefully you did that. Hopefully you paused it and tried it for 4 minutes. Let's talk about it together. So for increasing, decreasing, I need to make a sign chart of my derivative. I need to figure out when my first derivative is positive and when it's negative. And to begin that process, I got to think about when is my derivative going to be equal to 0 and when is it going to be undefined. So with this fraction, the only way for a fraction to be equal to 0 is if the numerator is 0. But the numerator is 4. That's never going to be 0. So my derivative never equals 0. Okay, so then I got to figure out when is my derivative undefined. F prime of x is undefined when the denominator is 0. And that happens when x is 0 from this term and when x is 6 from this term. So when x is 0 and 6. So we take those values and plot them on a number line. So we have 0 and we have 6. All right, so now I'm going to make a sign chart of the first derivative. And it's helpful to just write each of the factors that shows up in my first derivative as a row. So that includes the 4. So 4 is one of the factors. I have 4. Let's see, we have x to the 1/3. And then we have 6 minus x to the 5/3. And then once we have those, then we'll be able to put them all together and write down what our derivative sign is. And based on our derivative sign, I'll be able to tell if my original function f is increasing or decreasing. Okay, so let's make our sign chart. Okay, I'm going to split up these columns. All right, so looking at the signs now, with 4, that's just a positive number. So this is going to be positive the whole way. With x to the 1/3, this will be positive when x is bigger than 0. So it's positive on this side of 0. And it'll be negative on the other side of 0 when x is less than 0. With 6 minus x to the 5/3, for this to be positive, the x value needs to be less than 6, because that will make 6 minus x be positive. So to the left of 6, this is positive. And to the right of 6, the 6 minus x will be negative. And when I raise a negative number to the 5/3 power, that'll still stay negative. Okay, so now I have to put these together. Okay, so 1 negative and 2 positives makes a negative. Same thing in this last column. This will be negative. And 3 positives, that'll make a positive. Okay, so when our derivative is positive, the original function is increasing. It's going to be going up. When the derivative is negative, the original function is decreasing. So it's decreasing, it's going down. Same thing here, decreasing, it is going down. All right, so we are ready to state these intervals. So our original function f is increasing on that middle interval from 0 to 6. And f is decreasing. F is decreasing on the interval from negative infinity to 0, union 6 to infinity. Okay, now I'm going to box this. So this is where my function is increasing and where it's decreasing. One thing that I want to go back and comment on is when we make these sign charts, it's also important to consider the domain of the original function. And with this original function, the domain is all real numbers. There's no value of x that would present a problem when I plug it in. Because when I look at these fractional powers, that 3 on the bottom means I'm cube rooting. And I could cube root a positive number, I could cube root a negative number, I could cube root 0. Okay, sorry, there's one exception. The one thing that's not in the domain is going to be 6, because that makes the denominator be 0. But otherwise, everything else is just fine with this function. Okay. If there had been a domain restriction, like, oh, x is not allowed to be less than 0, it can't be negative, then I wouldn't have even bothered with the signs over here to the left of 0. All right, so if we look at part B of this question, that's asking me to classify the critical numbers. Okay, so if I look at this, there's one thing I'm going to have to be careful about. Let me get to that in a second. So when I look at 0, my function changes from decreasing to increasing. So that would give me a local min. Local min if it goes from decreasing to increasing. Okay, local min here. And I need to check. I need to check that 0 is actually in the domain of the original function. Because if it wasn't, it wouldn't be a local min. Because there's not even a point on the graph if it wasn't in the domain. Okay, but with 0, it is in the domain. I can plug it into the original function. So for b, I'm going to start to write my critical numbers. So far, for a critical number, we have x equals 0. And maybe we might add 6 to this. But right now, with the x equals 0, we have seen that there is a local min. A local min at x equals 0. I'm going to box that since my original function f changes from decreasing to increasing. And also because it's continuous at that critical number. This question also asked me for the value, like the local extreme value, which means I want to know the y value at this critical number. So the value would be, what is f of 0? What do I get when I plug 0 into the original function? And if I do that, it turns out I get 0. So that's my local min value. Okay, what about at x equals 6 now? So if we look at our number line at x equals 6, my function changes from increasing to decreasing, so that looks like it would be a local max. But I have to be careful. Going back to the original function, 6 is not in its domain. I can't plug 6 in because it makes the denominator 0. So there isn't even going to be a point on the graph where x is 6. So it definitely can't be a local max. It turns out that means 6 is not a critical number because it's not in the domain of the original function. All right, so let's write that down. X equals 6 is not in the domain. It's not in the domain of f, and because it's not in the domain of f, this means it's not going to be a critical number. And if it's not a critical number, then it can't be a local max or a local min. We'll see what happens with x equals 6 graphically later. It turns out what's happening is there's a vertical asymptote, and a vertical asymptote, you can change from increasing to decreasing without there being a local max. Okay, let's move on to part C. C is asking us to find the intervals of concavity and any inflection points. And here was our second derivative. So again, I want to give you a chance to try this. So pause the video for 4 minutes to try this question on your own first. 4, 3, 2, 1. Pause it for 4 minutes to try it. Alrighty, so hopefully you did that. Hopefully you paused it and tried it for about 4 minutes. Let's talk about it together. Okay, so we need to first figure out when is our second derivative now going to be equal to 0, and when is it undefined. So with this fraction, it's going to be equal to 0 when the numerator equals 0, and that happens when x equals 1. I should just do a quick check and make sure that that doesn't make the denominator 0, because if it made the denominator 0, it would make the whole fraction undefined. Okay, but when I plug 1 into this, it doesn't make the denominator 0, so that's good. Okay, and I also need to find when is my second derivative undefined. This is undefined when the denominator is 0, and that happens at x equals 0 and 6. Okay, so we take all of these values and put them on a number line. So even if these numbers are not in the domain of the original function, they still go on the number line. There are still places where the second derivative sign may change. So 0, 1, and 6. Okay, and I'm going to put each of the factors of my second derivative as a row. So let's see, we have 8, we have x minus 1, x to the 4/3, and then we have 6 minus x to the 8/3. Okay, and then once we have those, we'll be able to combine them for our second derivative, and then write down the original function if that's concave up or down. Okay, so let's separate out some rows. Separate out some rows, and then I'll separate out some columns. Okay, so now let's do our signs. 8 is just a positive number, so this is going to be positive the whole way. With x minus 1, that changes sign at 1. To the right of 1, when x is bigger than 1, x minus 1 is going to be positive. And to the left of 1, x minus 1 is going to be negative. With x to the 4/3, we got to be a little careful. Because, so let me write this in the margin maybe. With x to the 4/3, I don't know, let me put it here. So x to the 4/3 means cube root of x being raised to the 4th power. So with the cube root of x, I can plug in a positive number or a negative number or 0. But when I raise it to the 4th power, this is an even power. This is an even power. So the output can't be negative. It can't be negative, and that's why I have to be careful there. So x to the 4/3 is actually positive the whole way through. Okay, similarly with 6 minus x to the 8/3, I have this even power, this 8, and that'll guarantee that the output is never negative. So that's going to be positive on all of these. Okay, so now when I combine these to form the signs of the second derivative, when I have just one negative sign, that'll give me a negative. Same thing here, just one negative sign, that'll give me a negative. And then all positives will give me a positive. Here's what all positives give me a positive. Okay, and when the second derivative is positive, that means the original function is concave up. Here as well, it's concave up. But when the second derivative is negative, the original function is concave down. Here as well, it's concave down. So let's write these down as intervals. So original function f is concave up on, so we have this interval from 1 to 6, and we have this interval from 6 to infinity. But if we go back and look at our original function f of x, this function is not continuous at x equals 6. 6 is not in the domain because it makes the denominator 0. So as a result, with these intervals, even though they're consecutive, they're sort of back-to-back intervals where it's the same concavity, we cannot combine these into one, since our original function f is not continuous at x equals 6 at that cut point. Okay, let's do concave down now. So f is concave down on, so there's two consecutive intervals again. Let's see, one of them is negative infinity to 0, and the other one is 0 to 1. The other one is 0 to 1. And with these, there's another reason why I can't combine these. This one's a little bit trickier. It has to do with the second derivative. And with x equals 0 makes the second derivative undefined. And it turns out there's something weird or something interesting that's going to happen with the graph because the second derivative is undefined there. Okay. So with these, we can't combine them since our second derivative, f double prime of x, is undefined at x equals 0. I think this one's going to become more clear once I draw a picture. So I'm just going to comment right now. See the picture below once we get to drawing the picture. Alrighty, so let's box these. So we got where it's concave down, where it's concave up. Now we're ready for inflection points. So for inflection points, these are places where my function changes concavity, but where the function is still continuous. Let me write that better. Inflection points. Okay, so if I look up to my sign chart here, the concavity changes at x equals 1. So x equals 1. I got to make sure, though, that my original function is continuous there. So let's go back. So here is our original function. And with x equals 1, that's definitely in the domain of this function. And this is the type of function that we know. So our function is going to be continuous at x equals 1. The only place where this is discontinuous is when x equals 6. Okay, so for x equals 1, the concavity switches and f is continuous here. F is continuous at x equals 1. This question didn't just say find the x values of the inflection points. It said find the inflection points, which means get me the x and the y value. So get me the whole point. Okay, so we got to find the y value. The y value is going to be f of 1. I got to plug 1 into the original function. And if we do that, we will end up with 1 over 5 to the 2/3. All right, so our point, that's coming from just plugging in 1 into the original function. So our point, the x-coordinate's 1, the y-coordinate is 1 over 5 to the 2/3, and that is our inflection point. Alrighty, so for part D of this question, let's now find any vertical or horizontal asymptotes. So here was the original function, and let's do vertical. So our vertical asymptotes with this function are going to come from the factors in the denominator that don't cancel. And in this case, that's this 6 minus x to the 2/3. And what makes that be 0 is x equals 6. So x equals 6 is going to be the equation of our vertical asymptote. The more technical reason is, if I think about this in terms of a limit, if I do the limit as x approaches 6, and if I were to just plug 6 into this function, I'm going to get a non-zero on top over a 0 on the bottom. And that means I do the one-sided limits. And when I do the one-sided limits, they'll either be positive or negative infinity. And that's giving me this vertical asymptote. All right, so let's do horizontal asymptotes. So horizontal ones now. So for these, I'm going to first rewrite my function. Because both of these are to the 2/3 power, I can do a one big 2/3 power over of x over 6 minus x. And now we have to do the limit as x approaches infinity of this thing and as x approaches negative infinity. So as x goes to infinity of x over 6 minus x to the 2/3, we had this property of limits when our outer function is continuous, and the outer function here is actually x to the 2/3. When that's continuous, I can move the limit inside. So I'll get this big 2/3 power, and then the limit is now inside it. The limit as x goes to infinity of x over 6 minus x. And now on that limit, I can use my shortcut for limits of infinite limits of rational functions, where I keep the highest power term on the top and the highest power term on the bottom. So that'll give me the limit as x approaches infinity of x over negative x. And that just simplifies to give me -1. So overall, I will end up with a -1 to the 2/3 power, and that is just 1. All right, so now we have to do the limit as x goes to negative infinity, and we can show that similarly, the limit as x goes to negative infinity of our function will also be equal to 1. Okay, so the horizontal asymptote, there's just one of them here, and its equation is y equals 1. All right, so we have horizontal asymptote, we have the vertical asymptote at x equals 6. I'm ultimately sort of gearing up to graph this thing, and the last piece of information I want to find is the intercepts, and then I will try to put it all together and graph it. So let's do y-intercept and x-intercept. For the y-intercept, we need to set x equal to 0. Okay, so we get y equals f of 0. We've actually done this already because I think we had a local min when x equals 0. When we plug 0 into our function, we get 0 out. Okay, now, so that's going to be our y-intercept. So our y-intercept, I'm going to write it as a point. The x-coordinate is 0, and now we know that the y-coordinate is 0. Okay, I might also be able to see like, wait, this is also an x-intercept. But to be very thorough, I should find my x-intercepts because maybe there are others besides this one. Okay, so for the x-intercept, we set y equal to 0. So we'll have 0 equals our function, x to the 2/3 over 6 minus x to the 2/3. And now what I could do is I could multiply both sides by this denominator. And if we do that, we'll get 0 equals x to the 2/3. And the only way for x to the 2/3 to be equal to 0 is if x equals 0. Okay, so this is telling us, well, we just have one x-intercept. The x-intercept is 0, 0. Okay, so we got our intercepts. Just turns out that the intercepts are at the origin. Now we are ready for part F. which says to use the info from A through E to sketch the graph. Okay, so the idea here is I'm going to combine the sign charts of the first derivative and the second derivative, because I want to know when is the function sort of increasing in concave up, when is it increasing in concave down, those combinations, so I can get the most accurate sense of what the picture looks like. Okay, so I'm going to make one sort of big number line, and on this big number line, I put a tick mark at any number that I put a tick mark at for the f prime number line and the f double prime number line. So here is the number line for the first derivative. I put a tick mark at 0 and 6 there. So on our new number line, we will have to put a tick mark at 0 and at 6. I also need to include tick marks at anything I had a tick mark at in this f double prime number line. So let's look at those. So the f double prime number line, well, we had 0, 1, and 6. So two of the same numbers, but one new one at 1. So I also need to put a tick mark at 1. Okay, tick mark at 1. And then I'm going to keep track of, well, my first derivative and what its sign was, and the second derivative and what its sign was. And based off of those, I will then write down the shape of f. Alrighty, so if I go to my first derivative graph, the first derivative was positive only between 0 and 6, and it was negative everywhere else. So here as well, in my first derivative, I got to make it positive between 0 and 6. That's in both of these regions, between 0 and 6, and is a negative everywhere else. And with my second derivative sign chart, let's see, this was negative to the left of 1 and positive to the right of 1. Okay, so let's draw that. So it's negative to the left of 1 and positive to the right of 1. Okay, so what does this tell us about the shape of f? So if the first derivative is negative, that means my function is going to be decreasing. When the second derivative is negative, that means my function is concave down. So I got to draw something that's decreasing and concave down, and that is going to look like this, decreasing concave down. I'm going to do one more of these slowly, and then I'm going to do the other ones quickly. Okay, so next column, first derivative is positive, that means my original function is increasing, and the second derivative is negative, which means the original function is concave down. So that will look like this, increasing but concave down is that sort of shape. Okay, I'm going to ask you to now pause the video for 1 minute and see if you can fill out the remainder of these shapes. 4, 3, 2, 1, quick 1 minute pause. See if you do these other two shapes. Alrighty, let's talk about it together. So from 1 to 6, first derivative is positive, so f is increasing. Second derivative is positive, so it's concave up. Increasing concave up looks like this. Then the last interval would be decreasing concave up. Decreasing concave up looks like that. All right, I want to put all this information together to draw a picture now. All right, so now we're ready to graph this function. So I'm going to label it y equals f of x. And I'm going to draw some axes on my y-axis and my x-axis. And I'll put some tick marks. So I'll go 1, 2, 3, 4, 5, 6, 7. In the negative x direction, 1, 2, 3, 4, 5, 6, 7. On the y direction, I'm not going to put tick marks because I don't really know y values of my function. Okay, so what I'm going to do next is let's draw in those asymptotes. I know there's a vertical asymptote at x equals 6, and there's a vertical one, sorry, yeah, that was a vertical asymptote at x equals 6, and there's a horizontal one at 1, so horizontal asymptote at 1. And now we can draw in the intercepts. Our intercept was at 0, 0. This is the x-intercept and the y-intercept. And looking at the shapes of our graph from this number line above, to the left of 0, our graph has this shape. Okay, so I'm going to draw it having that shape to the left of 0, and it's going to get really, really close to that horizontal asymptote as x goes to negative infinity. Okay, in between 0 and 1, it has to have this shape, this increasing concave down shape. Okay, let me also label this point. This is 0, 0. And now from 0 to 1, it needs to have this shape. Okay, and I'll put a dot there. Because when x equals 1, we actually know the coordinates at this point. We figured it out already. This was 1 comma 1 over 5 to the 2/3. And 5 to the 2/3 is going to be bigger than 1. So 1 over 5 to the 2/3 is 1 divided by something bigger than 1. That's going to be less than 1. That's how I know that that point is below this horizontal asymptote. Okay, and at 1, our graph switches to being concave up. It's still going to be increasing. Okay, so it's got to go like this, and it's going to approach this vertical asymptote. Notice it's totally fine for a graph to cross a horizontal asymptote. Because all an asymptote is it's just something that the graph gets close to at the ends. So at the ends, over here, it's getting really, really close to it. But far away from it, it's totally fine if the graph does things like, cross that asymptote. Okay. And then to the right of 6, our graph has this decreasing concave upward shape. That's going to be something like this. And that is our graph.